algebra. Unit 5, Lesson 5. We are still talking exponential decay. Remember in last lesson we talked about, my tablet's not awake. We talked about decay is when we get smaller. Oh, you guys are going to watch me. Oh, there it is. Nope. All right, I'm going to pause it. Be right back. All right, it came back. So decay is when something gets smaller. We talked about exponential growth, where whatever value we're talking about gets exponentially bigger, like doubling. If I put $5 in the bank, hold on. If I put $5 in the bank, it's my initial value, and it doubled every year. Okay, my function would look like this. Now we're talking about decay, where if I bought a car for really cheap car for $1,000 and it depreciated, say it lost a third of its value, a third of its value, that means there'd be 2/3 remaining. Okay, so that is decay when our factor, which is our multiplier, is less than 1. Actually between 0 and 1. It's a fraction between 0 and 1. And here is growth when our factor is a number greater than 1. Okay, all right, let's get into the lesson. So use the patterns you noticed to complete the table. Show your reasoning. So table A, 2.5, I'm going to 10 to 17.5 to 25. It's not really doubling. Let's see, if I added, where's my calculator? There it is. Okay, if I did differences, so I'm just going to do subtraction. Yep, so plus 7.5 plus 7.5, just checking the math, 17.5 plus 7.5 is 25. So I'm growing by a constant addition, okay? It's not a factor because a factor would be multiplication. This would be 32.5 and then 25. So really I've got my initial amount and I'm adding 7.5 each time. So if I'm at 25, I'm going to multiply 7.5 times 25 plus my initial amount. Okay, this is linear. Very important that we know. When I add the same amount each time, I'm linear. In essence, yeah, this is my slope. And this is my y-intercept. All right, let's look at table B. 2.5 to 10, that's 7.5. So I'm adding 7.5 here, but this is not adding 7.5. So the linear addition does not work. All right, so let's try multiplication. If I take 10 and divide by 7.5, I get 4/3. Let's test it. If I do 10 times 4/3, I get 40/3, so that didn't work. 2.5 times 4 is 10. Not sure what I just did. So times 4, and then 40 times 4 is 160. So times 4 is 640. So if I wanted the 25th spot, if I wanted the y value for the 25th x, I've got my initial value times, I'm quadrupling it to the x. This is going to be 2.5 times 4 to the 25th power. 4 caret 25, big number, times 2.5. Sorry, it is a huge number. 2.81 times 10 to the 15th in scientific notation. That's a lot of zeros. All right. So we talked, that one's linear and this one is exponential. And notice it's exponential growth because it's getting bigger and bigger and bigger. It's not decay. All right, in order to control an algae bloom in a lake, scientists introduced some treatment products. Once the treatment begins, the area covered by the algae, A, in square yards is given by the equation A equals 240 times 1/3 to the T. All right, so that 1/3 tells me that we're decaying. Okay, that algae bloom is going to get smaller and smaller. So in the equation, what does 240 tell us about the algae? 240 is this, so that is our initial amount. What's amount mean? It's our initial area. Right, and what does the 1/3 tell us? So, sorry, 240 is our initial amount, so I'm going to write up here. 1/3 would be the area still covered from the previous week. Okay, so there's 1/3 of the area covered in algae remaining. Okay, we've taken away 2/3 of it. There's 1/3 remaining. All right. Create a graph to represent A equals when T is 1, 2, 3, and 4. Think carefully about how you choose the scale for the axes. If you get stuck, consider creating a table of values. We're going to create a table of values. So I've got time, which is in weeks, and area, which is the algae. So I'm doing 0, 1, 2, 3, and 4. And my equation is 240 times 1/3 to the T. So when when T is 0, anything raised to the 0 power is 1, so I'm left with 240. 240 times 240 times x to the first power, 240 times 1/3 to the first power is 80. And then 240 times 1/3 raised to the second power, 26.7. I'm rounding. That's actually going to be a 2/3 in there, but it's okay. 240 times 240 times 1/3 to the third power. Ooh, look how quickly we're getting smaller and smaller. 240 times 1/3 to the fourth power. Okay, I could have rounded that to 3. So our time, we're going to say 0, 1, 2, 3, 4. We're going from 240, 50. That's going to be too small. 1, 2, 3, 4, 5, 6, 7, 8. I think this might work. That's 100. 1, 2. It's not. This is 200. So we're going to say this is about 250. So at 0, we're just there. Okay, at 1, we're at 80. That's 100, that's 75, so 80. At week 2, we're at 26.7. That's 25. 8.9. 2.96. Okay, this is not discrete. I can draw a curve through it. Because it's not like at each week, oh, I can't draw curves with my pen. It's not like at each week that it just magically, boom, that algae disappears. Like, oh guys, it's been 7 days. Oh, that's terrible. It's been 7 days. You know, 2/3 of you have to disappear now. It's a gradual decrease. And it's going to keep on getting closer and closer to 0, but it'll never actually reach 0. Okay. About how many square yards will the algae cover after 2.5 weeks? So 2.5 weeks would be 240. It's going to be somewhere in between here, but I can actually calculate it. So 240 times 1/3 raised to the 2.5 power is going to be 15.4, which is between 26 and 8.9. Okay, it's not exactly halfway between. If I do 26.7 plus 8.9, if I take the average of that, 26.7 plus 8.9 divided by 2, I get 17.8. So if I found the halfway point between 2 and 3, which is about 2.5, mathematically I get 17.8. If I use the equation, I get 15.4. Exponential is not linear, so I can't do the average between those 2 points because it's not a linear growth or decay. The scientists estimate that to keep the algae bloom from spreading after the treatment concludes, they will need to get the area covered under 1 square foot. How many weeks should they run the treatment in order to achieve this? Yep, I am getting a few of you. I will remind you that you need to put just a tiny bit of effort into this. Okay? Those bonus quiz points are not given out free just for sending me an email and saying, hey. All right, insulin in the body. Here students make sense of a graph representing a situation characterized by exponential decay. So let's do it. So scientists, a patient who is diabetic receives 100 micrograms of insulin. The graph shows the amount of insulin and micrograms remaining in his bloodstream over time in T minutes. Scientists have found that the amount of insulin in the patient's body changes exponentially. How can you check if the graph supports the scientist's claim? I don't need to check. It doesn't appear to be linear. Okay, this curve is characteristic of an exponential function. This time being decay, because it's getting closer and closer to the x-axis. So what this means is each minute, if I went between minute 0 and minute 1, I've lost 10 micrograms. So I went from 100 micrograms to 90 micrograms. And then minute 2, 81 micrograms. So if it were linear, I'd subtract 10 and then I'd subtract 9. Okay, that's not how the exponential growth works, or exponential decay in this case. So I can't keep on subtracting. The subtraction needs to be consistent. So I am most definitely multiplying. So here I'm doing 8 times 0.9 is remaining. And if I test that, 90 times 0.9 is 81. And what I really did, I divided 90 over 100, and that's 0.9. And then I divided 81 over 90, and that's 0.9. And then I could divide 72.9 over 81, and that's 0.9. Okay? So that's how you find your factor. And it's also a way to double check that it's an exponential function. Okay, next question. How much insulin broke down? How much insulin broke down in the first minute? What fraction of the original insulin is that? So how much insulin broke down, that is, if that's 0.9, that's actually 9/10. And that's how much remains. Well, how much broke down? We lost 1/9 of it because it needs to make a whole. Okay? No, not 1/9. Golly, guys, I'm sorry. I got my numbers backwards. 1/10 broke down. You guys probably roll your eyes at me. 9/10 remains. Okay. How much insulin broke down the second minute? Well, another 1/10 of the insulin broke down. And 9/10 remains. I could also say that 10 micrograms, that's not how you do micrograms, broke down. Oh. And here I could say 9 micrograms. I did micrometers. That's really funny. I haven't finished my coffee yet. Maybe I shouldn't record math videos without finishing my coffee. So there 9 micrograms broke down, which is 1/10 of the amount. 9/10 remains. What fraction of insulin remains in the bloodstream for each minute that passes? Explain your reasoning. All right, 9/10 remains. Got ahead of myself. I know that if 1/10 broke down, 9/10 remains, because if I add those together, I get 10/10, which is a whole. All right, if you notice, whenever we do these exponential decay fractions, how much remains and how much left removed. If I add those together, it equals 1. Okay, it's a pizza pie. If I take out 1 slice, 9 slices remain. Put them together, I've got a whole pizza pie. All right. Complete the table. So we're doing how much remains. So our equation is going to be insulin equals initial amount times how much remains raised to the time. Okay? So I always test out my equation. I can do 100 times 9/10 raised to the 0 power. Easy. 100 times 9/10 raised to the first power is 90. 100 times 9/10 raised to the second power, 81. I'm going to skip x equals 3 or time equals 3 because I know it's working. So now I can do raised to the fourth power, and I get 65.61. And then 100 times 9/10 raised to the fifth power, 59.049. Describe how you would find how many micrograms remain after 10 minutes, after m minutes. I got ahead of myself again. So I've got 100, my initial amount, times the fraction of how much remains to the 10 minutes. And that's going to be 34.9 micrograms. And then m minutes raised to the m. I raised it to the t up there. And we're at our summary. Okay, I'm going to remind you these summaries are amazing. Okay, it's a great way to study for a test. I used to cut and paste them all and put them in your Blackboard. Nobody was looking at them, so I stopped. If you'd like me to do that, just let me know and I can. But that's our lesson for today.